Hello and welcome to Software Architecture course. In this lecture, we will continue with architecture patterns and we will cover an important architecture pattern called blackboard architecture. So let's look at the context and the problem for blackboard architecture. Here, the requirement is that a set of heterogeneous and really specialized modules, that's important, heterogeneous and specialized modules, which dynamically change their strategies. And why do they do that? Because they need to respond to some unpredictable events. So these are highly non-deterministic. The whole strategies are highly non-deterministic. The application really does not know what is that event based on which they need to respond to. So the problem here is that there is no deterministic solution to process the raw data, and therefore it is required to exchange algorithms, take decisions dynamically, do some intermediate computation. In fact, there might be a requirement that these partial problems that are solved to eventually reach the goal, these partial problems might have different data representation. No predetermined strategy is there to present and solve a particular problem. In fact, it is very different from the functional decomposition, where the sequence of activations are more hard-coded. Here nothing is hard-coded. Here one has to take the decision more dynamically. One needs to deal with uncertain knowledge. What are the forces or constraints or requirement? You cannot do a complete search of the solution space. Sometimes, because clearly the solution space is really large and a complete search of solution space is actually not feasible at all. Algorithms might be different for different parts of the solution. One algorithm would use a result of another algorithm. Then input, intermediate data, output, everything can have different representation. And most importantly, even if you enforce that input data etc. to have uniform representation, even then there is no strict sequence between algorithms, so one can run them concurrently. Sequences might be altered. Examples are one early project called Hearsay in 1980. This was basically a speech recognition problem where the human speech is or voice is recorded on a recording device, and that's processed and that's recognized, and obviously it's a project for English speaking person, so it is recognized and then it is translated to an English sentence, which you see today even in a mobile device. So this was a project in 1980 that requires multiple set of components to work together. Each of them have different algorithms, starting from signal processing to translate signal to English word. Modern example of vehicle identification and tracking systems, robot control like navigation, environment learning, reasoning about the environment, finding out the destination route and plan for the best possible route and then move. Modern machine learning algorithms for complex tasks. You must have heard of a recent Jeopardy challenge, which was actually a problem that was taken up by IBM Labs, IBM Watson Labs. So in this Jeopardy challenge, Jeopardy is basically a popular quiz program in the US, and what happened was IBM built a machine which took part in this Jeopardy challenge, and in fact it had beaten the best possible, in fact it became the winner. So here the thing is that this particular machine was asked the question exactly the way the questions are asked to a human, and it had to respond, give answer within the time limit, and it actually won. This is truly a very complex task. Adobe OCR based text recognition problem. Modern compilers, they tend to be more blackboard oriented than pipeline. So these are some of the examples. Lunar landers and then those spacecraft mission control kind of softwares, the control algorithms, the control softwares that are there in Mars lander. So those are basically primarily based out of Blackboard type architecture. So in Blackboard architecture pattern, they have basically two main components. One is the central data structure, which is called the Blackboard, and there are a set of components which are operating on the Blackboard. So system control is entirely driven by the Blackboard state. So let's look at these components in detail. As I said, the Blackboard is basically the shared data structure where the solutions are actually built and even partial solutions are kept. Then there is a control plan that encapsulates the information that are required to run the system. Again, this control plan is accessed and updated by the control knowledge sources. Then the domain knowledge source .domain KS, these are concerned with solving a particular problem. Example is that suppose in the hearsay project there could be a domain case that deals with only, let us say, signal handling. Another domain case might be involved in just error correction. Another domain case might be involved in just translating these signals to English word. Control knowledge source, it adapts the current control plan. Basically, control knowledge source is dealing with the control plan. It adapts the current control plan and to the current situation. It modifies and move the whole system accordingly. So the control component essentially selects, it configures and executes different knowledge sources. So the domain case do not get executed by themselves. They are basically controlled by these control components. Let's look at the class diagram of this particular pattern. In fact, from now onwards and more so in design patterns, you will see this kind of class diagrams to illustrate the solution. So as you see here, there is something called a Blackboard controller that uses a set of knowledge sources. There is a control plan and there is a Blackboard. So Blackboard contains the partial solutions. So as you can see here, there is a solutions, which is basically a set of solutions which are accessed and which are updated. This Blackboard controller is a master controller that runs in a loop, and it monitors a change in the Blackboard. In fact, it can even run in an infinite loop. It monitors a change in the Blackboard. It activates the next appropriate knowledge source. What is the next knowledge source? This strategy may depend on the control data. This knowledge source is basically a collection of highly specialized modules. Each knowledge source is different, and each of them has a set of triggering conditions, when to start, when to stop. In fact, the code that contains in these knowledge sources, they basically fetch the data from the Blackboard, or it can update the Blackboard. But important part is they do not interact with each other. They only interact only through the Blackboard. Control knowledge source, as I said earlier, it encapsulates the control plan and it updates the control data, such as it estimates the progress, can compute the cost to decide which knowledge source to be fired. So by cost, it means that whether if a particular knowledge source is executed, whether it is worth executing it, will it really expedite the progress, or it might create some other problem. So it takes that decision, and then based on that it fires that particular knowledge source. It has a control plan. So this control case essentially would be updating these control plans, and Blackboard controller will basically, in that run loop, it will basically control and orchestrate these knowledge sources. So in an example of automated robo navigation, one can first define the high level goal of the robo is to visit a set of places as soon as possible. So this can be divided into a set of sub goals. For example, the sub goals could be that deciding on a sequence of places to visit, to compute the best route, to navigate the constraint of, in fact, to navigate is in itself is another sub goal, but navigate with a set of constraints in a real fast way. So these three sub goals could be domain knowledge sources. So here one knowledge source could be basically there to decide what are the set of places that one can visit, what is the best route, how to navigate, satisfying a set of constraints real fast. So, and plus there are many other sub goals, and then this control KS would possibly choose the best possible knowledge source here, and then use the output of these knowledge sources to decide the next path. For example, if it gives a set of best routes, not just one, then which one to choose? For that, maybe it is a control case that decides which one to choose, and then call the navigate module with the best possible route. And of course it continuously checks whether it is closer to the goal. Here the goal is to visit a particular place or maybe a set of places. How close the robot is to the particular place, this could be the goal, and this could be the even completion criteria. So there are of course benefits and there are of course liabilities. Benefits are, it is definitely useful for scenarios where solution is really not known and highly dynamic. One needs to try different strategies. It certainly supports for modifiability. Each knowledge source is strictly decoupled, so you could replace one with another. Reuse of KS is certainly possible here. Even when the data is noisy, one can have a fault tolerance built in. How? Because one can have multiple set of domain knowledge sources which can process data. One could be for the good data, another could be for the bad data. So depending on the quality of the data, the control path can possibly, or the control knowledge source can possibly choose the right module to process data depending on the quality of the data. So if such a architecture is not there, then the whole system might fail. If the system is just hard coded to process the data of only certain quality, so the moment data quality falls below that and becomes noisy, the traditional systems will fail. Here it might try different alternatives. Liabilities are, it is really difficult to test. In fact, there is no good solution that is guaranteed. You have no idea what is called a good solution in many cases. So there are too much of computational overhead in rejecting wrong solutions, because here one may have to backtrack and then again start all over again, so which essentially means rejecting those old solutions. Of course it has high development effort. Another important part is that this Blackboard, because it is accessed concurrently by many components, Blackboard must be synchronized. Therefore overall parallelization might be difficult because all of them are dependent on the Blackboard. So that's it for the Blackboard pattern. In the next lecture we will continue with more such architectural patterns. Thanks.